Hi, this lesson is about logarithmic differentiation and the derivative of inverse trig functions. So we start with differentiation. It's a process where you take the derivative of a function by first taking the natural log of both sides of the equation, then expanding the function by applying the logarithmic properties or laws before actually taking the derivative. The process of applying the logarithmic properties or laws simplifies the overall function, making taking the derivative a little bit easier. So here's an example where we will use logarithmic differentiation. So we have y equals e to the 2x times x squared minus 5x to the 7th. So as explained above, step 1 is to take the natural log of both sides of the equation. Then, step 2, I'm going to use the logarithmic properties or laws to expand this. So first I'm going to take that product and separate it into two separate logarithms. So I have ln of e to the 2x plus ln of x squared minus 5x to the 7th. Then I'm going to use the power law for logarithms, where you can put the exponent in front of the logarithm. So the 2x ends up in front of ln of e, and the 7 is written in front of ln of x squared minus 5x. Now you can further simplify because ln of e is equal to 1, so here you're really just dealing with 2x plus 7 times that polynomial. So when I'm ready to take the derivative, I have to take the derivative of the left and right side of the equation, and on the left side, you need to apply your chain rule because you're taking the derivative with respect to x, and it's not just y on the left, it's natural log of y. So I take the derivative of natural log, which is 1 over y, times the derivative of y, which is y prime or dy dx. On the right side, remember, this is just 2x because ln of e is 1, and the derivative of 2x is 2, and the derivative here, I have to apply chain rule to ln of x squared minus 5x. So it's 7 times the derivative of the outer function, the ln is 1 over x squared minus 5x, times the derivative of the inner function, and the derivative here is 2x minus 5. All right, so what that leaves me with is that I have now 2 plus 7 times 2x minus 5 over x squared minus 5x. So in the next step, I'm going to get a common denominator. And that common denominator is x squared minus 5x. So that means the 2 gets multiplied by x squared minus 5x. Now I need to simplify the expression in the numerator by first distributing the 2 and distributing the 7. That's what you get on this next line. So my new numerator is 2x squared minus 10x plus 14x minus 35 over the common denominator. And then remember, I need to solve for y prime. So what I did was I multiplied both the left side and the right side by y, so that on the left side the y's cancel, and I'm left with just y prime on the next line. But we know what y is equal to. Y is equal to the original function, and the original function is e to the 2x times x squared minus 5x, so I replace y with that value. And this x squared minus 5x cancels with one of these, so your final answer is e to the 2x times 2x squared plus 4x minus 35 times x squared minus 5x raised to the 6th power. So this same problem could have been done right from the very beginning using the rules that we already know. You don't have to use logarithmic differentiation in all cases. And if we did this without logarithmic differentiation, it would be product rule first, because it's e to the 2x times x squared minus 5x to the 7th. And within product rule, you would have chain rule because e to the 2x is a composite, and then another chain rule for x squared minus 5x to the 7th, which is also a composite. In the end, if you had taken a different approach, we would get the same answer as we got here in this box. Okay, so here we're asked to use logarithmic differentiation to find dy dt for y equal to t to the 3t squared. So, same first step. Take the natural log of both sides, and on the right side, we can rewrite it using our logarithmic laws as 3t squared times ln of t. So now I'm ready to take the derivative, and on the right side, I have to apply product rule, and the work for that is here. I'm letting f equal 3t squared, g is ln of t, so f prime is 6t and g prime is 1 over t. So when we take the derivative of both sides of that equation, on the left side I get 1 over y prime. Again, using chain rule there, the derivative of ln is 1 over y, and the derivative of y is y prime, or dy dt. Then I plug into my product rule. So it's fg prime, 3t squared times 1 over t, plus g f prime, so it's ln of t times 6t. Now this t cancels with one of the t's in the 3t squared, so I'm left with 3t plus 6t ln of t. Final step is to multiply both sides by y so that y prime is alone, and replace y with what y is equal to, so that's what I did right here. So I'm left with 3t plus 6t ln of t, all multiplied by t to the 3t squared. Okay, so let's move on. Here's another. We're going to use logarithmic differentiation to find dy dx for y equal to x to the sine of x. So again, I take the natural log of both sides. So I have ln of y equals ln of x to the sine of x. Using the log laws for powers means that I can rewrite the sine of x in front of the logarithm. So I am now multiplying sine of x times ln of x. And now I'm ready to take the derivative. On the right side, I have to use product rule. On the left side, it's chain rule. So the derivative of ln of y is 1 over y prime, or dy dx. And on the right side, I did f g prime, so that's sine of x times the derivative of ln, which is 1 over x, plus, and this is g f prime, so my g is ln of x, and my f prime is cosine of x. So next step is to multiply both sides by y, and then I got a common denominator for the sine of x over x and ln of x times cosine of x by multiplying this one by x over x. So I end up with sine of x plus x ln of x cosine of x times the value of y, which we know y is equal to x to the sine of x. So logarithmic differentiation can be used in any type of problem, but it is particularly helpful when you have a variable raised to a variable, just like we have in this example, or in this previous example where we had a variable raised to another variable expression. Okay, the second part of this lesson is on inverse trigonometric functions and their derivatives. So as a reminder, there are 6 inverse trigonometric functions, and inverse trigonometric functions are used to find the angle of a corresponding trig function. So if I have y is equal to sine inverse of x, that's going to be the inverse function to sine, then you can rewrite that as x is equal to sine to the y, where x is the angle. So x would be, where y is the angle. So your answer for your trig function is your angle. That's what you're taking the sine of. And then all the other ones have the same relationship. You have cosine inverse If y is equal to cosine inverse of x, then x is equal to cosine of y. We have tangent. If y is equal to tangent inverse of x, then x is equal to tangent of y. And the same is true for cosecant inverse, secant inverse, and cotangent inverse. Remember, there are different ways to indicate inverse trigonometric functions. Other notation would be, instead of saying sine inverse, you could say the arc sine of x, or the arc cosine, arc tangent, arc cosecant, arc secant, and arc cotangent. They mean the same thing as using this other notation, which is read as sine inverse. So this is not sine to the -1 power, it is sine inverse. And just keep in mind that negative is not an exponent, so that is not equal to 1 over sine of x. So that's important for you to keep in mind. So here are derivatives of our inverse trigonometric functions. And so the derivative of sine inverse is equal to 1 over the square root of 1 minus x squared. The derivative of cosine inverse is almost the same, except it's got a minus in front of it, so it's -1 over square root of 1 minus x squared. The derivative of tan inverse is 1 over 1 plus x squared. Cosecant inverse is -1 over x times square root of x squared minus 1. Notice that here the x squared and the -1 is in a different order than here. Sometimes people get that mixed up. And then the derivative of secant inverse is almost the same as cosecant inverse, except this one has a negative and secant inverse doesn't. So secant inverse is 1 over x times the square root of x squared minus 1. And cotangent inverse looks a lot like the derivative for tan inverse, again, except it's got a negative in front of it. So it is equal to -1 over 1 plus x squared. So just like all other formulas I have given, highly recommend that you memorize these. Really helps to speed you up and to recognize things when you see them. That will be especially important when you get to integration and you're going in the other direction. And so you might see things like this in your problems, and you would need to recognize them as having a relationship with the inverse trig functions. So we're going to prove that the derivative of sine inverse is 1 over the square root of 1 minus x squared. So I just told you that was true by giving you that list of formulas above, but now I'm going to show you where it comes from just by using some techniques that we already know how to use. So the original function is y equal to sine inverse of x. So I know that I can rewrite this inverse function in terms of its corresponding sine function as x is equal to sine of y. Then if I take the derivative of both sides of this equation with respect to x, I have the derivative of x with respect to x and the derivative of sine of y with respect to x. Well, dx over dx is just 1. But on the right side, it's implicitly defined, so this will be the derivative of sine, which is cosine of y, times the derivative of y, which is y prime. Now, if I solve for y prime, divide both sides by cosine of y, and you get that y prime is equal to 1 over cosine of y. Now, I know from the Pythagorean identities that sine squared of an angle, so I'm going to call it y to match with what I'm doing here, sine squared of y plus cosine squared of y is equal to 1. And if I solve that identity for cosine of y, you'll get that cosine of y is equal to the square root of 1 minus sine squared of y. So I am replacing this cosine of y with what the right side says here. But I know that sine of y is equal to x. We stated that originally. So when I replace sine of y with x, you'll get that the derivative is 1 over the square root of 1 minus x squared, which is exactly what we wanted to prove. Okay, so we're going to do something similar. We're going to show that the derivative of cosecant of y, the derivative of cosecant of x is equal to y prime equal to -1 over x times the square root of x squared minus 1. So it will be a very similar process to what I did above. So first we start with y equals cosecant of x, and we rewrite that in terms of x. So x is now equal to cosecant of y. Then I take the derivative of both sides with respect to x. So dx is 1. But the derivative of cosecant of y is the derivative of cosecant, which is negative cosecant cotangent, both of y, times the derivative of y, which is y prime, or dy dx. Okay, so if I solve for y prime, that means I divide both sides by negative cosecant y cotangent y, which is what I get here. Now that doesn't exactly look like this, but now we're going to do some substitution. So I know that cosecant of y is equal to x, so I can immediately replace that with x. But to deal with the cotangent of y, I turn back to one of the Pythagorean identities. And so one of those identities is 1 plus cotangent squared of y equals cosecant squared of y. And if I solve this for cotangent, you'll get the square root of cosecant squared of y minus 1. And so that means that I can now replace that with cosecant square root of cosecant squared of y minus 1, but we know that cosecant of y is equal to x, so if I plug that in, it'll be x squared minus 1, which is exactly what we got right here. And that was what we needed to prove, and so we're done. Now that could be done for all of the inverse trigonometric functions, a similar process of just showing where it's coming from. All right, so now let's actually take the derivative of an inverse function, an inverse trig function. So here we have y is equal to sine inverse of 2x cubed. So this would be a problem where we have to apply chain rule, where sine inverse is the outer function and 2x cubed is the inner function. But remember that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Okay, but I don't just have x, I have 2x cubed in this problem. So the 2x cubed is going to replace the x. So that's what I did first. I took the derivative of sine inverse. So that would be 1 over the square root of 1 minus 2x cubed raised to the second power. The same way here, the x was raised to the second power. Now 2x cubed is raised to the second power. Times the derivative of the inner function, and that would be 6x squared. So if I multiply the 1 and the 6x squared and expand the 2x cubed to the second, or multiply it out, you get, this is a result, 6x squared over the square root of 1 minus 4x to the sixth. All right, so here's another. I want to find dy dt for y equal to tan inverse of the square root of t. This is another problem where I would have to use chain rule, where tan inverse is the outer function and the inner function is square root of t. So as a reminder, the derivative of tan inverse of, and I'll call it t just to match with what I have here, is going to be 1 over 1 plus t squared, which could also be written like this. Addition is commutative, so it could be written in either one of those two ways. Okay, but this time my variable is root t. So root t is going to get plugged in there. Okay, so when I take the derivative of the outer function first, it's the derivative of tan inverse. That would be 1 over 1 plus square root of t squared times the derivative of t to the 1/2, which would be 1/2 t to the negative 1/2. We're applying power rule there. And when I put this all together, square root of t raised to the second power will just give me t. and this one can go down into the denominator along with the 2. So I'm left with dy dt is equal to 1 over 2 square root of t times 1 plus t. Okay, so that's it for that lesson. Give the homework a try. Good luck.